These are the notes for AP Calculus on the topic of additional infinite series problems. So first let's look at what it means to be the difference between conditional convergence versus absolute convergence. And this applies to alternating series. So an infinite series converges absolutely if both the positive term series and the alternating term series converge. Then either way it's converging, so it converges absolutely. However, sometimes the alternating series will converge, but not the same series if it wasn't alternating, referred to as the positive term series. So an infinite series converges conditionally if only the alternating term series converges, but not the positive term series. So let's take a look at a couple examples of this. State if each of the series converges absolutely or conditionally. All right, so we can see this is an alternating series, so let's first apply the alternating series test to see if it converges at all. So we'd find the limit as n approaches infinity. This is just like a 1 over n squared. And that'd be 1 over infinity squared, so that's 0. So that's the first condition on that, which is really the divergence test, or nth term series test. The limit as n approaches infinity has to equal 0 of everything except for that negative one that causes it to be alternating, the rest of the formula here to find each term. But that it requires one more thing to see if the alternating series converges, and that's that the terms keep getting smaller. So if we substitute in 1, we'd get 1 over 1 squared, so that'd be 1, so a sub 1 would be 1. A sub 2, if we substitute in 2, would be 1 over 2 squared, so 1/4. If we substitute in 3, it'd be 1 over 3 squared, so 1/9. So indeed the terms do get smaller, so we can say the alternating series converges. However, we want to see, well, does the positive term series converge? In other words, if it was just 1 over n squared, if we just had this series right here, this series from n equals 1 to infinity of just 1 over n squared, would that converge or not? And you can see this fits a p-series test, so p is equal to 2, and since that's greater than 1, this converges by the p-series test. So since both the alternating series converges and the positive term series without the negative 1 to the end converges, this one converges absolutely. Now let's take a look at another one here. So again, we can find the limit as n approaches infinity of, this is just 1 over n. So when you substitute in infinity, it's 1 over infinity, which is 0. So that's the first condition of the alternating term series. And then if we find the first three terms, a sub 1, a sub 2, a sub 3, we plug in 1, you get 1 over 1 is 1. Substitute in 2, 1 over 2 is 1/2. 3, 1 over 3 is 1/3. So again, the terms keep getting smaller. So again, this alternating series converges. That's the alternating series test we're using. Then we want to see, well, if we didn't have that negative 1 to the n, sometimes it's n plus 1, in this case just n, let's see, would it converge if all the terms were positive? In other words, the sum from n equals 1 to infinity of just 1 over n. Well, you can see this also fits the p-series test, but in this case, p is equal to 1. And since that's less than or equal to 1, this diverges by the p-series test. So here's a case where the alternating series does converge, because the limit as n approaches infinity is 0, and the terms do indeed keep getting smaller. However, if it wasn't alternating, it would be 1 over n, and it would diverge by the p-series test, So this is the one you would say converges conditionally, on the condition that it's alternating, basically. If it's not alternating, it won't diverge, not converge. So again, if both the positive term series and the alternating series converge, that's called converging absolutely. However, if only the alternating series converges, but not the positive term series, if it wasn't alternating, then it converges conditionally. All right, let's take a look at some other problems now. So this one says, okay, we've got g of x equals this series from n equals 1 to infinity of x to the 3n divided by n factorial. And we want to write the first 4 non-zero terms and the general term for g prime of x. Well, for g prime of x, we first need the g of x, right? So we've got our general term right here of g of x, but we need the first 4 non-zero terms of the derivative, so we probably need the first 4 at least terms of the original function. So to find this, if we just substitute in, starting with n equals 1 here, substitute in 1, the g of x would equal, if we substitute in 1, that's going to be x to the third over 1 factorial is just 1. Plus, if we substitute in 2, it would be x to the sixth over 2 factorial, just 2 times 1 is 2. Plus, if we substitute in 3, 3 times 3, x to the ninth over 3 factorial. 3 factorial is 3 times 2, which is 6. Plus x to the 12th, 4 times 3. And then over 4 factorial, well, 4 factorial is 4 times 3 times 2. That's 12 times 2, so that's 24. And then plus, there's our first 4 non-zero terms. The general term we're given right here in the formula, x to the 3n. That's how we found the first 4 non-zero terms over n factorial. Okay. But that's g of x. Now it asks for g prime of x, so we just take the derivative using the same derivative rules we already know. Derivative x cubed using the power rule would be bring down the exponent 3 and reduce the exponent by 1, so 3x squared. Same thing on each of these. Bring down the 6, but divided by 2, that's 3. Reduce the exponent by 1, that's x to the fifth. Bring down the 9, you get 9/6 reduces to 3 halves, so that'd be 3 x to the 8th over 2. Plus, bring down the 12, divided by 24, that reduces to 1 half, so x to the 11th over 2, or you could write 1 half x to the 11th. Plus, now notice we use the power rule on all these, so we'd use the power rule on this as well. So just like we brought down the exponents on all of these, we do the same thing with this exponent, which happens to be 3n. So it'd be 3n. And then what happened to the exponent after that? Well, it got reduced by 1 using the power rule, so it'd be 3n minus 1. But notice it's n factorial, there's no x there. That's just a constant, depending on what n we're plugging in, so that would just stay n factorial. So there's the first 4 non-zero terms and the general term for g prime of x. Next example says, let n be the third degree Taylor polynomial for e to the negative 4x about x equals 2. So you can see it is a Taylor one, not Maclaurin, because Maclaurin are always about x equals 0. And we want to know, well, what's the slope of the tangent line at x equals 2? All right, well, the slope of the tangent line, that comes from the derivative, doesn't it? So we don't have to write the whole tangent line, just the slope of it. So let's first write our third degree Taylor polynomial. It says P is our third degree Taylor polynomial. If you want, you can call it P sub 3, just to remind you it's a third degree of x would equal. Well, notice here's where you want to have memorized e to the x pattern, which starts, it's like sine and cosine, but it's all positive and it's not alternating. So the 1 plus, normally this would be x to the first, but now it's negative 4x to the first, plus normally it would be x squared, but now it's negative 4x squared over 2 factorial. A third degree Taylor polynomial, you gotta keep going. This is second degree. Remember, degree refers to the highest exponent. So one more term, negative 4x cubed over 3 factorial. So there's our third degree Taylor polynomial. We'll stop with an exponent of 3. And let's go ahead and simplify this first. So the third degree Taylor polynomial simplified would be 1. This becomes minus 4x. That's negative 4 squared is 16 divided by 2 is 8. And we've got x squared plus negative 4 cubed is negative 64 over 3 factorial 3 times 2. And then we can see the 2 goes into 64 32 times. So we end up with, actually this is not plus, it's minus, isn't it? Because our term is negative 32 over 3, and then x cubed. There's our third degree Taylor polynomial. And then if we want the slope of the tangent line to the graph of p, well this is p, so we know we need the derivative to get the slope of our tangent line, remember? So now we find the derivative of this first. So p prime, this is the prime of x. Well, the derivative of 1 is 0, derivative of negative 4x, negative 4. Derivative of 8x squared, using the power, would be 16x to the first. And then minus, power along here. When you bring down the 3, notice that reduces out with the 3 on the denominator. So you're just left with negative 32 x squared. Oh, and I realized I forgot one important thing here. I was treating this like a Maclaurin one. I should have probably done that in this step, but we can still do it right here. When it's about x equals 2, instead of x, all these x's are going to be x minus 2. So it'd be negative 4 plus 16x minus 2 minus 32x minus 2 squared. I could have put that in here as well. So this was actually should have been 1 minus 4x minus 2 plus 8x minus 2 squared minus 32 over 3x minus 2 cubed. Notice that when we take the derivative, it would give us the same thing, because thankfully this didn't require using, the chain rule here didn't affect our answer at all, because the derivative of the inside function is just 1. So here the derivative would be negative 4. Here you'd bring down the 2, it would be 16x minus 2 to the first. Bring down the 3, it'd be negative 32x minus 2 squared. So you get the same thing, just don't forget, like I did there almost until the very end, that it's not a Maclaurin series, it's Taylor about x equals 2. And that's important, because that's going to change our answer. Notice it said the slope of the tangent line at x equals 2. So now we would substitute 2 into this, which is going to give you a different answer than if you had left it like this. So you get negative 4 plus 16, 2 minus 2 minus 32, 2 minus 2 squared. But notice, when you substitute 2, this one's 0, this one's 0, so those wipe out, so all that's left is negative 4. So the slope of our tangent line at 2 is negative 4. All right, let's take a look at the next one. So this is probably the most challenging of all of them that we're going to look at today on this section of notes. Is write the first 3 terms and the general term of the power series for this. Okay, so we've got the integral with x, and then we've got cosine of t cubed. Well, wouldn't it be nice that when we have 0 to x and we got cosine of t cubed, that kind of looks like the second fundamental theorem, except in order to apply the second fundamental theorem, you'd have to take the derivative of this. So let's go ahead and do that. Take the derivative of this integral and see what happens. All right, so now this fits the second fundamental theorem. Of calculus. Which basically relates the derivative and integral are reverse operations, they're like inverse functions, and they essentially cancel each other out. Okay? As long as this is a constant, which it is, so we don't have to flip our integral, making it negative, and we don't have to use the chain rule because this is just x. So this one fits the second fundamental theorem exactly. Remember, the only thing that happens is x replaces the t. So the derivative of this would be cosine of x cubed. That's it. Basically stays the same function. Now, you want to remember, well, cosine of x cubed is just a modification of cosine x. And remember, cosine is an even graph. So it involves all the even exponent terms. We'll agree that's even. So the first one would be x to the 0, but that's just 1. And then it alternates between positive and negative here, so that's how you remember it's alternating. Normally, it'd be the next even one would be x squared over 2 factorial. However, in place of x, we've got x cubed here. So instead of x squared, like we normally have for just cosine x, it would be x cubed squared. Okay. So there's our first two terms. We want the first three terms, and then it alternates to positive. It normally would be x to the 4th, but now it's x cubed to the 4th over 4 factorial. And then it says the general term also, so plus dot dot dot. And then notice it alternates first of all. So in our general term, we're going to need negative 1. And it's either to the n or n plus 1. Let's see. If it's to the n, we substitute in 0. We get negative 1 to 0 is positive, and our first term is positive, so that's fine. And when you plug in 1, negative 1 is the first negative, so the next term is negative, and so on. And then normally, this is just x to the 2n, because we want to keep the exponents even here. However, instead of x, we've got x cubed, so it's x cubed to the 2n. Divided by 2n, that same number of the exponent factorial. So let's simplify this. So cosine of x cubed would be 1 minus, this is x to the 6th over 2 factorial, just 2, plus that's x to the 12th over 4 factorial is 4 times 3 times 2, so that's 24. And I'll simplify this one would be negative 1 to the n. This becomes x to the 6n over 2n in parentheses factorial. So you might think, well, that's our answer. However, that's not what it asks us to find. Not the power series for cosine of x cubed, but the integral from 0 to x of cosine of t cubed. So that means in order to get our final answer, we need to integrate this, right? Because we took the derivative to get this. This is really the derivative of our power series. We did that to simplify it, but now to get back, we want to just integrate. So when you integrate 1, you get x minus x to the 6th over 6 times 2, so that's 12, plus, no, x to the 6th. I didn't integrate that at all, did I? You add 1 to the exponent, so it would be x to the 7th over 7 times 2 is 14, plus x to the 13th over, when it gets really large like this, sometimes I'll leave it just 13 times 24. You can work that out if you wanted to. Plus, and then on this one, same thing's going to happen. We'll still have negative 1 to the n. And then look what happened on these. When we integrate, we added 1 to the exponent, right? So it'd be x to the 6n plus 1. You can put in parentheses to make it clear that whole thing's the exponent. And notice we divided by that exponent. Here we divide by 7, here we divide by 13. So it'd be divided by 6n plus 1. And then we still have times the 2n factorial. So we basically took the derivative to help us simplify it, to get it to just be cosine of x cubed. But then we integrated to get back what we started with. So this would be the power series for the first 3 terms and the general term. All right, let's look at the next one. It says, let f be a positive continuous decreasing function. If the integral from 1 to infinity of f of x dx equals 4, notice this is a finite answer. It converges. Does this series converge or diverge? Well, this exactly fits our integral test, remember, and says if the definite integral is finite and converges, so will the series. And if the definite integral diverges, so will the series. They both converge or they both diverge. In this case, this converges since we got a specific answer, finite answer of 4. So we can say this series here, f of n converges. Then it says, if the series converges, which it does, state if its sum is greater than or less, oops, I forgot the word is, sum is greater than or less than 4, and justify our answer. Okay. So it converges by the integral test. since this integral converges. But to see whether it's less than or greater than 4, you have to think of, probably the easiest way to think about it is graphically. So if we sketch what this graph could look like, just a rough sketch, notice that we know it's positive, continuous, and decreasing. Well, if it stays positive, and continuous and decreasing, well, in order to stay positive, it would have to be concave up, wouldn't it? Because if it was linear, it would eventually become negative. If it was concave down and become negative, the only way it can stay positive if it looks something like this, concave up, so it's always above the x-axis. And then notice the difference is the definite integral from 1 to infinity just gives you this exact area, right? And we found that exact area there is 4. Well, we want to know, well, would this series be greater than or less than 4? In other words, would it under or overestimate this? So the way to see that is, well, notice unlike the integral, which is using all these infinitely thin rectangles, this one is not. It's only using integers when you have a series like this. You plug in 1 friend, then 2, then 3. So the first number you substitute in is 1. That would give you a height here, and then that would give you your first rectangle. Then you substitute in 2, do the second one, then 3. So you can see it's going to follow the graph, but because we're just using integers on a series, each time those rectangles, because the graph is decreasing, overestimate the definite integral. So we can say, and its sum is greater than 4, since, because it said a just answer, well, it's since the fact that it's decreasing, since f is decreasing. Or you could also say since f prime of x is less than 0, because that's what's causing it to decrease. Notice if it had been an increasing function, then these would have actually underestimated it. All right. Now this next one says the Maclaurin series for the function f is given by this. So this one is a Maclaurin series. And it says, well, based on that, what's the value of f of 3? Well, f of 3, let's go ahead and substitute and see what happens. So f of 3, we notice we're substituting 3 for x, not for n, would be the series from n equals 0 to infinity, negative 2 over 3 for x to the n. Well, if you take a look at that, you can see, well, we're just keep multiplying by another negative 2/3 each time. You substitute in 0. The first term would be negative 2/3 of 0 would be negative 2/3. The second term, when you plug in 1, would be, sorry, the first term when you substitute in 0 is 1. The second term when you substitute in 1 is negative 2/3. The third term when you substitute in 2 is negative 2/3 squared is 4/9. So if you can see the pattern, every time we're multiplying by a negative 2/3. So this is geometric, where r, the common ratio, is negative 2/3. And for a geometric series, remember r has to be between negative 1 and 1, and negative 2/3 is. So this converges. Do the geometric series test. But it says, what's the value of this? So since it's geometric, remember the formula for a geometric series that converges to find its sum is the sum of a sub 1 over 1 minus the common ratio. In this case, a sub 1, our first term was 1, divided by 1 minus the common ratio we just figured out is negative 2/3. So you get 1 over, that's 3 over 3, the negatives cancel out there, plus 2 over 3 gives you 1 divided by 5/3, which is the same as 1 times the reciprocal, 3/5. So this series equals 3/5. So that's what f of 3 is. Usually when they're asking you for the sum of a series, most of the time it's going to be geometric, because that one we have a nice formula for, unlike the other tests that just tell you if it converges or diverges. This next one's written a little differently. It says, well, we've got this series, and a1 equals 8. And a sub n plus 1 divided by a sub n is 1/3 for all integers n greater than or equal to 1. Then what is this series? Okay. All right, so this is saying if we start with a sub 1, that would mean if a sub 1 is here, a sub 2 is here, right? And that has to equal 1/3. Well, we know a sub 1 is 8, so we can say a sub 2 over 8 equals 1/3. Then to solve for the second term, you could cross multiply. That would give you 3 a sub 2 equals 8. Divide by 3, a sub 2 is 8/3. So now we know the first term is 8. The second term is 8/3. And if we find one more term, we can figure out what the pattern is, I think. So now we could also use this formula. Now that we know a sub 2, we could say this is a sub 2. So this one would be one more. A sub 3 would equal 1/3. But we know a sub 2 from right here is 8/3. So a sub 3 divided by 8/3 equals 1/3. Cross multiply, you get 3 a sub 3 equals 1 times 8/3 is 8/3. Divide by 3, that's like multiplying by 1/3, gives you 8/9. So there's our third term. So what's the pattern here? Well, it's dividing by 3 or multiplying by 1/3. So it's geometric. So we keep multiplying by the same constant of 1/3. And then, what's our common ratio is 1/3. Notice that's not a coincidence that it's a 1/3 right there as well. Because this is saying the term one more than this one, you just divided by the previous term is 1/3. So this divided by 8 is 1/3. This divided by this is 1/3. Because basically it's going in reverse, right? If you take the term and a sub n plus 1 divided by the term before it, you'll get that common ratio of 1/3. It's just a different way of writing it. And so it says what this sum is, which means basically equals. So you just use the geometric series formula again. A sub 1 over 1 minus the common ratio r. The first term here is 8 divided by 1 minus 1/3. Well, 1 minus 1/3, this is 3/3, minus 1/3 is 2/3. And 8 divided by 2/3 is the same as 8 times 3/2. So that's 24 divided by 2 is 12. Okay. Next one a little different. It says the infinite series has an nth partial sum. So remember, partial sums mean adding up the first so many terms. So here, if n was 10, that'd be the sum of the first 10 terms. If n was 20, that'd be the sum of the first 20 terms, and so on. But it gives you a formula for that partial sum. So it says, does this series converge or diverge? If it converges, find its sum. Okay. So what we can do to figure this out is, well, what's happening to see if it converges or diverges? Well, the number of terms n is going to infinity. So let's see what happens. The limit as n approaches infinity of 2n over 5n plus 3. Well, if we substitute in infinity, we get 2 infinity over 5 infinity. The plus 3 is negligible. Then the infinities reduce out, and we get 2/5. So this partial sum, as the number of terms goes to infinity, is approaching 2/5. So we got a specific number, which means this series converges. And what's the sum? We just found it. And its sum is 2/5. Whereas if this hadn't been a finite number, if we got an infinity here, then that would have told us that this series, in fact, diverges. So I'll go one more. This one, the infinite series, has the nth partial sum, -1 to the n. Well, again, we want to see, does this series converge or diverge? This one's a little trickier. If it converges, find its sum. Well, if we look at this, we'll have, as, again, the partial sum, we want to see what happens to that partial sum as n approaches infinity. So we have an infinite number of terms. So the limit as n approaches infinity of -1 to the n. Well, we can see this is an alternating series. And And all that's left, the rest of the problem is just 1. So the alternating series test says the first thing you do is find the limit as n approaches infinity of everything but the negative 1 at the end of just 1. Well, there's nothing to plug infinity to. Limit as n approaches 1 of 1 is just 1. And because that's not equal to 0, this diverges by the alternating series test. It didn't say we had to justify it, but that's why it would diverge. Or another way to think about this is that you keep plugging in the next number here into this series. It's going to be negative 1, then it's going to be positive 1, then negative 1, then positive 1, negative 1. It never settles on a specific value. It's diverging. And that concludes the notes for AP Calculus on the additional infinite series problem.